Today I want to go over the Chapter 5 presentation, give you all the study guides. Don't worry, they're not nearly as long as the ones for Chapter 4. Promise. If you look at Moodle for next week, let's talk about that real quick. I want y'all to know what's going on. So for next week, today we're going through Chapter 5. And I've asked y'all to go ahead and start going through Chapter 5 with the study guide and maybe do the quiz. Because when we meet next week, we've got 3 packet tracers to do. We're also going to go ahead and do the midterm exam. I want us to do the midterm exam and then start Chapter 6 instead of stopping in the middle of Chapter 6 to take an exam that includes Chapter 6 before we've actually started really digging into it or doing any lab work on it. So we're technically doing that a week early. Now, since we're doing it a week early, you get to use your notes and you get to use Cisco Academy to take the midterm. You don't get to use YouTube or Google Answers, but you have all those other resources at your disposal to take the midterm. The midterm grades are due the 21st, which is the next week. So anything that you need to make up, or if you figured out how the grading works and now you look back at your grades and you go, well, I really wish that was higher. Anything you want to redo and turn in has to be done by the day before I need to turn in grades. So that's not next Thursday, but the next. So be thinking about that and going through your grades so that I have time to give an accurate midterm grade for you, because I have all those things already graded and ready to go. Does anybody have any questions about that? If you don't need to make anything up, don't worry about it. But if you feel like you'd like to redo some things, you still have that opportunity. So that's what we're going to be doing next week. Again, the midterm exam is going to be chapters 1 through 5. There's 10 questions randomly chosen from each chapter. So it will be 50 questions. You will have Cisco Academy and any notes that you've taken available. So it shouldn't be very difficult. I'm not going to make you do packet tracers. I'll make you do that for the final, but not for the midterm, because we're still getting acquainted with packet tracer. Okay, Chapter 5 is about Ethernet. We're going to talk about Ethernet as a protocol. We're going to talk a lot. Yes, sir?
The test? The makeup test?
You'll have to do it after.
Oh, okay.
After this, yeah. I don't want attention to be divided. We're going to talk a lot about the operation of switches, which is really important, and then later on we'll talk a little bit about the operation of routers so that you know how those work. We're going to talk about the address resolution protocol, which is going to come up a lot throughout your networking career, and that is all going to be parts of Chapter 5. So first off, let's talk about the Ethernet protocol. So we spoke a little bit when we talked about the OSL model about encapsulation and de-encapsulation. So when you hear the term encapsulation, you're thinking about part of a packet being encapsulated in another layer, and de-encapsulation is the taking off as it goes to another layer. So thinking in those terms, when we talk about Ethernet, Ethernet is actually kind of part of the physical and the data link layer part of the OSL model. And the standard for Ethernet is 802.2 or 802.3 is the physical standard. So you might hear those standards come up. Ethernet is the most widely used LAN technology. It has to do, again, with those bottom 2 layers of the OSL model. And it's in this family of networking technologies. We talked about the different organizations that come up with standards for what things look like, and that is IEEE. So it supports a very varied data bandwidth from anywhere from 10 to 100,000 megabits per second, which is pretty fast. 100 gigs is quite fast, right? So Ethernet's going to define the layer 1 and the layer 2. And there's 2 sublayers within the data link layer. which I think we've talked about the MAC address and the LLC, or the MAC layer and the LLC, I should say. So the two things that the MAC layer does, it does first off data encapsulation. So that's the process of grabbing a frame and then wrapping it up so it can be, grabbing bits and putting them in a frame, I should say. Or grabbing a packet and stripping it down so it's just a frame that we talked about previously. We have the video of the guy in the different hats as he was going down the layers, adding and taking things away from the packets. And we've also got the media access control. So the responsibility of that layer is placing frames on the media and then taking frames off of the media. So it controls access to the media, hence the media access control, right? So it communicates directly with this physical layer underneath. Ethernet 2 has some different fields in it when you look at what a frame looks like. This is kind of what you see. There's a little more to it, which we'll talk about in a minute. But you've got the preamble, which is basically saying a frame is about to start, pay attention. Then you've got a destination address, a source address, the type, which is generally Ethernet 2. There were more than one Ethernet type, but Ethernet 2 won out. There is the data field that actually has the stuff in it that you're trying to send. And then there's something called the frame check sequence. So that's an integrity check to make sure that data wasn't changed during transmission. That's all you need to know about frame check right now. It's this big mathematical formula. You're not expected to know that, but you do need to know what frame check is. There's a couple different kinds of fields. The minimum Ethernet frame size is 64 bytes. We call that a runt sometimes because it's the smallest available size. And then the maximum frame size is 1,518 bytes, which we would call a jumbo frame. So if you see that terminology, that's what they're referring to. We're not going to go very far into depth in this week. When we get into like chapter 7 and we start subnetting, you're going to be expected to do a lot of math conversions. They're very easy conversions comparatively, so if you're not good at math, that's okay because I'm not either, but I can totally subnet all day. So don't feel bad if you see things like this and go, what is she talking about? Because we will get there. If you look to the left-hand side in this column, you see the decimal column. So we have a decimal-based number system. So decimal means it's based on 10, right? You have 10 possible combinations, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So you have 10 options in the decimal system. So binary, computers are speaking in ones and zeros. They understand is something on or is something off, and that's it. So that's why it's got 2 options. 0 is off and 1 is on. Another option is the hexadecimal numbering system. So this is based on a factor of 15. So you have the decimal values 0 through 9, and then you have the letters of the alphabet A through F, so A, B, C, D, E, F. Those are all valid numbers or valid characters in the hexadecimal format. And when we start looking at MAC addresses, they're in hexadecimal, so that's why this is being brought up in this chapter. For right now, I just want you to understand the concept. For example, if you look at the decimal value of 2, in hexadecimal, it's still 2 because 2 is a valid number in hexadecimal, okay? If you look at once everything restarts, you have 0 through 9 available in hexadecimal, but if you wanted to represent 10, you would use the letter A, because 10 and A are equal, okay? Just a different way of saying the same thing in a different numbering system. That will be important when you start to look at MAC addresses. So the layer 2 MAC address is a 48-bit binary value that's expressed as 12 hexadecimal digits. So the first 3 bytes of that, the first half of the MAC address, is what's called the OUI, or the organizationally unique identifier. So that means whoever the person is that's making the NIC is assigning a MAC address to it, and every company has their very own first 3 bytes, the first 3 parts of that address. So if you're Dell, every single MAC address that you have starts with the first 3 things, and that indicates it's from Dell. If you're Netgear, if you're Apple, whoever's manufacturing these NICs, the first 3 bytes of that address are the same for that company. They have their own specific identifier. Now the last part of that, the other half of the address is the vendor assigned. So all the MAC addresses will have the same first 3 addresses for that company, but the last 3 parts of that address will be different. So that's the part that makes it unique. So remember, 24 bits is for the organization, and it will be the same for everything produced by that organization. And then the last 24 bits are going to be something that's unique just to that card. No 2 MAC addresses should be the same. It could happen. They are supposed to kind of keep track of which ones they're giving out. But ideally, a MAC address would be a completely unique address, and nobody else would ever share it. So let's look at what it looks like to process a frame. So the NIC is going to view information to see if the destination MAC address matches the device's physical MAC address that it has stored. And if there's no match, it's just going to disregard the frame. But if there is a match, the computer's essentially going to say, hey, this is addressed to me, it's for me, so I'm going to go ahead and process it. So when you look at this diagram down here, something is being sent from the source, which is all A's, to the destination, which is all C's. So what happens is A sends out a packet to everybody on the line, and it's not really meant for H2 or H4 because that's not who it's addressed to. But they're going to get the frame, they're going to look at it and go, well, that's not addressed to me, so I won't pay attention to it. Whereas H3 is actually the destination. It's going to say, this is for me, I'm going to go ahead and process the frame. That's what it looks like to process a frame on, this would be a bus network, when everybody received the frame, like if we had a hub, for example. So different manufacturers can represent a MAC address, and they have what's called different delimiters in them. So depending on who is putting the MAC address out there, it might look a little bit different. So one of the ways you'd see that is with dashes in between the characters. Another way would be with colons, not semicolons, not the one that's got the comma at the bottom, but just the 2 dots, this is the colon. And then with periods in between as well. So either way of viewing MAC addresses like that is valid. It just depends, you might see something different. So right now, I want you to pull up Command Prompt on your computer. You would do that by clicking the Start menu icon, type in CMD, hit Enter, and when the command prompt comes up, I want you to type in ipconfig/all. A bunch of y'all are already doing that. When you type in ipconfig/all and hit enter, you should get a really long list that pops up of all the interfaces, all the network interfaces on your computer, and all the information about those interfaces. But what I want you to do is scroll up to the very top where it will probably say local area connection. And then you'll be able to see your IP address, your MAC address, your DNS servers, your subnet mask, all the things that we've kind of talked about in class. So what does your MAC address look like? Does it have dashes, colons, or periods?
Dashes.
Dashes? Does everybody have dashes? What do all your computers have in common?
They're all Dell.
They're all Dells, right? So that's the way that Dell expresses their MAC address. Sometimes in Cisco stuff you might see things with periods in them. But that's just a glimpse to very easily be able to play around in there and see how your computer is connected. And some of that information can kind of be interesting. You'll see all kinds of things called virtual adapters and things like that. If you've ever worked with virtual machines, if you're in the operating systems class, those are virtual adapters. It's not a physical thing that's plugged into your computer, but it still has to have an address to it to be able to get on the internet. So you might see some things like that as well. So there's a little bit about the MAC address representations. A unicast message is sent from one source to one host. like from a host to the server in this instance. We've kind of talked about unicast before. But what I want you to see is that the unicast IP and MAC addresses are used by the source to forward the packet. So it's keeping track of the IP address and the MAC address of the source and destination, and that's going to become really important when we start watching a little bit more about how these things work. So the destination MAC and the destination IP address in this example both point to the server, and I can tell that because the destination MAC address matches the destination MAC address on the server, and so does the IP address. So it uses both of those pieces of information. In a little bit, we'll talk about why it needs both. The broadcast MAC address is sent from the source to all the hosts on the network. Now, something distinctive, if you look at this, if you look at your destination MAC address, you see it looks a little funny because everything is all Fs. So F is the highest hexadecimal value, right? It's the 15 of the decimal, right? So when you see something addressed to all Fs, that means it's a broadcast MAC address every time. The destination IP address, 255 is the highest value that can be in the octet of an IP address. So when you see something that's got 255 at the end of it, it's always a broadcast. It's a broadcast, not a MAC address, but it's also a broadcast IP address. So when something looks like that on the destination, that's indicating that it's going to all the hosts on the network. A multicast message is sent from the source to some of the people on the network. We talked a little bit about this a couple chapters ago, but these are hosts that have opted in to be able to see this transmission. So in this case, the destination MAC and destination IP both point to what we can call a multicast address, which is something that's been set up by the administrator ahead of time. When we start looking at different classes of addresses, if you're a little familiar with networking, there is a specific range of addresses that are defined as just being multicast addresses, and that 224.0.0.200 is in that range. So we'll talk a little bit more about that in chapter 6 and 7. So let's talk a little bit about the operation of switches, because switches are a big deal. They're everywhere. We need to know how they work. So a switch is a layer 2 device. So it is a data link layer device. It uses MAC addresses to make forwarding decisions. It just uses MAC addresses so far at this point. The MAC address table is sometimes referred to as a CAM table. We will be looking at MAC address tables as well. So let's talk about how a switch learns where everybody is connected to it. So you'll have a port with 24 switches on it. It has to, at some point, learn who all's connected to it, so it knows if it needs to send to someone, how it's supposed to get to it. So let's talk about how that happens. So this switch is going to kind of dynamically build up this MAC address table, because every time somebody sends something in on a port, it's going to look and see where is that source MAC address. So there's some really good examples in Cisco Academy that talk about this. So every single time a frame enters a switch, the same process occurs every time. So looking at this example when we're talking about learning MAC addresses, so in this instance, the computer A and computer D are going to talk to each other. So computer A is going to send in a frame. The switch is going to look and say, okay, attached to port 1, the source MAC address was 00-0A. They've simplified these addresses just so it's easier to look at. So now I know that whatever's on port 1, whatever computer or whatever device that is, has that MAC address. So now anytime anybody needs to send anything to computer A, I know where to get it. It's on port 1. So it'll kind of continue that as it goes along. So the destination MAC address is D. We know that because we're looking at the chart, but the switch has no idea. It says, how on earth am I supposed to get to D? I don't have any information about that at all. So what it's going to do is it's going to send a frame out to all the other people connected to the switch and essentially be like, are you this address? Because I'm looking for this address. So let me know if you are. So then D is going to reply back and say, well, now I know where to find A if I need it again. But also, I'm going to tell the MAC address of the switch, or the MAC address table of the switch, that's me. I'm the address that you're looking for. So go ahead and send the thing to me because that's my address. So that ends up on the MAC address table too. So you can see how this kind of starts to build by looking at the people that are talking. So now it's going to be able to understand if I need to talk to, if D needs to talk to A, it knows where to go to get it because it's in the switch's MAC address table. So the next time PCA sends another frame over to PCD, it's going to know exactly where to go. It's on port 4. Until somebody messes wiring around and changes something, but we have a way to get around that. But it's going to filter out those frames in that way, so it knows where it's actually supposed to go. There's several videos within this chapter. I want to show them to you because they're very, very step-by-step and good about talking about how frames move. This one is talking about routers or default gateways.
So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So the Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address, and because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame, which is not in its MAC address table, so it floods it out all ports. PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, and because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
Okay, so an important thing to note is that when you're sending something to a network that's not on your internal network, the MAC address is the MAC address of the router. You'll have test questions about that. That's an important thing to realize right now. Okay, so let's talk about frame forwarding. Forwarding is just another way of saying sending. So sending frames on Cisco switches. There's a couple different versions of frame forwarding. There's store and forward and cut through. So we're going to talk about the differences between the two. So store and forward receives the whole frame, and then it computes what's called the CRC, or the cyclic redundancy check. which is just a thing that says have any errors happened. It's for error detection. It's another mathematical formula. So the switch is then going to look up the destination, determine if it's got the right way to get to it, and then it's going to forward it out the correct port. So store and forward does the CRC check. That's what's indicative of that one. The cut through receives the frame before it's completely even received, and then the destination of the frame must be read, and then the frame is forwarded. So you notice that in cut through, there's no CRC check. There's no error detection in that way. So fast forward switching, this is a version of cut through switching. This is the lowest level of latency, meaning it immediately forwards the packet. It looks at the address and sends it on, and that's all there is to it. Latency means delay. So for something to have low latency means it works very quickly. Fragment-free switching is storing the first 64 bytes of the frame before it forwards it. Most of the errors that occur in frames are going to occur in the first 64 bytes because that's right before the data starts. That's where you have all the addressing and the type and the preamble. If you're going to have an error, it's probably going to be in that first part. So the fragment-free switching is there to try to do like a small error check on the things that might be the most prone to error, and then send the frame on its way. Speaking about switches, we've got duplexes and speed settings that we often see. A lot of times in troubleshooting, this is one of the things that goes wrong. Something was set to half duplex instead of full, and that made it suddenly very, very slow. So these are some settings on switch ports that we'll be doing in this class. There's full duplex, which means both ends of the connection send and receive simultaneously. And there's half duplex, which means only one of them can send at a time. So you could guess that half duplex would probably be the slower between the two. There's something on switches now called auto negotiation. That is found on a lot of newer switches and NICs, which basically says they're going to exchange information amongst themselves about the speed and about whether or not it's half duplex or full duplex, and they're going to figure out the best way to talk to each other. But a lot of times you'll find in packet tracers where you have to troubleshoot things, maybe something has been set to half duplex, and that's what's wrong with it. It really should be full. And there's an example of that. One switch is being full duplex, the other's half duplex, so they're having trouble communicating with each other. There's a function of switches called auto MDIX, which is going to auto detect the type of connection and then configure the interface according to the type of connection. So you hook up a switch to a switch. What kind of cable do you need?
Straight to. Oh, no, crossover.
Switch to switch, remember that's like devices.
Crossover.
Like devices are a crossover, but this auto MDIX is smart enough to say, I see that you're connecting two switches. I'm going to go ahead and just mechanically switch over the transmit and receive so you don't have to make a crossover cable. And that makes all of us happy because it means we don't have to make cables, right? This is logically kind of fixing this transmitting and this receiving pairs. Even if physically maybe it's not the correct switch, but it's going to fix that for us. So let's talk a little bit about ARP, Address Resolution Protocol. So we have two addresses when we're talking about assigning addresses to devices. We're talking about the physical address, which is the MAC address. It's the thing that we can't easily change. It's supposed to be unique just to our computer. And then we've got the logical address, or the IP address. The IP address can change. It can get statically assigned or dynamically assigned from a DHCP server, as we've talked about in the past. So what I want you to understand is that if your destination is on the same network, you're going to be talking in MAC addresses. You're going to be staying in that layer 2 area, in that Ethernet area. If you're talking about IP addresses, you're going outside of your local network segment. Then you're going to be talking about IP layer 3 logical addressing. So when the destination IP address is on a remote network, the destination MAC address be the address of the router, or the router's NIC, probably a better way to say that. So this is the first place it goes when it needs to go outside the network, right? So it would make sense that that would be the destination address. So ARP, or Address Resolution Protocol, resolves MAC addresses to IP addresses. That is the purpose of ARP. So in this example, we've got 4 computers. They all have IP addresses. They're connected to a switch. Since they're connected to a switch, I know that they're on the same network segment. They're on the same network, right? So PCH1 says I need to send information to 192.168.1.7, but I only have their IP address. I don't know what their MAC address is. Since we're staying on the local LAN segment, we need to know their MAC address if we want to talk to them, right? So ARP, again, another table. We're going to use ARP to find the MAC address that's mapped to the IP address. So we're going to find that match there. So if the IP address is on the same network, we're going to search the ARP table where it keeps all these things stored to figure out the destination. If it's on a different network, we're going to consult the router. And if we don't find an entry in the ARP table, we're going to go ask it. We're just going to say, hey, what is your address? So an ARP request is sent out when there's, it doesn't have an entry in the ARP table. We're going to see that when we do one of our packet tracers next week. So there is the target IP address, which is going to correspond with the target's MAC address. So it's going to be encapsulated in a frame and sent out. Something that's important to note is that routers will not forward out broadcasts, which makes sense because ARP is talking about MAC addresses, which are internal to the network, whereas IP addresses are external to the network. So if a router forwarded out an ARP request, they would essentially be asking the entire internet for a MAC address, which is, you wouldn't need to even do that, right? So here's a little bit about what it looks like to have an ARP request.
We're going to see PCA send an ARP request for the MAC address of PCC. PCA has an IP packet with the source IP address of itself, 192.168.1.110, and the destination IP address of PCC at 192.168.1.50. So it needs to know what the destination MAC address will be. Because the source and destination IP addresses are on the same network, the destination MAC address will be that of the destination IP address of PCC at 192.168.1.50. So PCA checks its ARP cache for the IP address 192.168.1.50. Because it is not in its ARP cache, it will put the packet on hold and create an ARP request. The ARP request contains the target IPv4 address. This is the IPv4 address which is known by PCA. And the target MAC address, which is unknown. This is what PCA is wanting to find out. The ARP request is sent as a broadcast, so everybody on the network will need to examine this Ethernet frame and process the ARP request. So PCA sends it to the switch. Because it is a broadcast, the switch will flood it out all ports except for the port that it came in on. PCB receives the broadcast, so it must process it, and its ARP process examines the ARP request. It compares its own IPv4 address against the target IPv4 address, and notice that they are not the same, so it doesn't need to send an ARP reply. The router R1 also receives this ARP request. Its ARP process examines its own IPv4 address and compares that against the target IPv4 address, and also realizes this is not its IPv4 address, so it does not need to send the ARP reply. By the way, routers will not forward ARP requests out other ports. PCC receives the ARP request compares its IPv4 address against the target IPv4 address, and notices that it is the intended target of the ARP request, that the target IPv4 address does match its own IPv4 address. So PCC will need to send an ARP reply.
Okay, let's see what that ARP reply looks like.
In the previous video, we saw an ARP request from PCA looking for the MAC address of PCC. In this video, we will see the ARP reply in response to that ARP request. PCC, when it received the ARP request, examined the target IPv4 address and compared it against its own IPv4 address, and noticed that it was the intended target. So PCC will generate an ARP reply in response to that ARP request. The ARP reply includes its own IPv4 address and its own MAC address. It is sent to PCA. ARP replies are sent as a unicast, so the destination MAC address is that of PCA. PCA receives the ARP reply in response to its previous ARP request. It takes the information, the sender IPv4 address and the sender MAC address, and adds that information to its ARP cache. PCA can now take the packet, the original packet destined for PCC, take that packet off hold, and has the information it needs to send that packet to PCC. So it takes the information from the ARP cache, the MAC address, and adds that to the Ethernet header as the destination MAC address. PCA can now forward this packet in the proper Ethernet frame onto PCC.
Okay, so now you've seen the ARP request and the reply and how they were both handled. So now anytime you see something referred to as remote communication or remote network, it's talking about something outside your local network, so it's probably going to be over the internet. So something a little different happens when we're talking about a remote network.
In this video, PCA has an IP packet, source IP address itself at 192.168.1.110, and destination IP address 10.1.1.10, which is an IP address on a remote network. So the destination MAC address will be that of its default gateway, 192.168.1.1, the router R1 in this case. PCA checks its ARP cache for that IP address, 192.168.1.1, and there's no entry with a MAC address. So it puts the packet on hold and creates an ARP request. The ARP request has the IP address of the router, 192.168.1.1, and the target MAC address is unknown. The destination MAC address of an ARP request is a broadcast. So it will be sent to the switch, and the switch will flood it out all ports except for the incoming port. PCB receives the ARP request, compares its own IPv4 address against the target IPv4 address in the ARP request, and notices it is not a match, so it is not the intended target. PCC receives the ARP request, compares its IPv4 address against the target IPv4 address, and it is not the intended target either. Router R1 receives the ARP request, compares its IPv4 address against the target IPv4 address, and it is indeed a match. It is the target of the ARP request. So router R1 will issue an ARP reply in response. It will include its own MAC address, 000D, along with its IPv4 address. The destination MAC address of the ARP reply is a unicast directed for PCA. So it is a destination MAC address of 000A, so PCA receives the ARP reply. PCA, when it receives the ARP reply, in response for its ARP request, sees the target IPv4 address and the target MAC address, and adds that to its ARP cache. It now has the information it needs to forward the packet which is on hold. So the destination MAC address is now going to be 000D, that of the router R1, its MAC address. And now PCA can forward the frame onto router R1.
So the difference here is when it got an ARP reply, it didn't actually get an address to the computer that it was expecting. It got information from the router where the router said, let me handle it. When you need to send something to 10.1.1.10, just send it to me and I'll forward it the rest of the way. So that's the difference that we see when we're talking about a remote network. So if a computer is changed, so let's say one of the computers on the other end of the cable dies, and we have to change it. If we have a different network interface card, we're going to have a different MAC address. So there can be changes made to these computers and to their MAC address. So we can remove entries from that ARP table so it doesn't try to send things to the wrong computer. So we have what we call the ARP cache timer. If something hasn't been used for a long period of time, it's just going to take it out of the table. It's going to say, I haven't sent anything to that link in 3 days. So it's probably different. I'm going to take it out of the table. And then we'll start this request and reply thing over again to see if we need to use it again. You can also manually remove things from the ARP table. If you want to, in a Cisco router, see the ARP table, you would have to click on a router, and then you would say show IP ARP, and it would give you a list of the table. So it would say the address, the corresponding MAC address, and then it would probably tell you how it got that information and what interface it shows up on. But show IP ARP is that command. If you did on a Windows PC and command prompt, as we did earlier, if you did ARP space -A, you can see the ARP table. So of course I want y'all to do that. Open up command prompt again and do ARP-A, and I want to get an idea of how many computers your computer has learned MAC addresses for.
What is it again, or, is it or, what I'm saying?
Yeah, ARP space -A.
You really want us to count all of these?
No. Is there 5 or more than 5?
More than 5.
Way more than 5, right? Okay.
We're talking about like 40.
Why do you think that is?
Because we're all in the same team.
Right? We're all in our own little space in here, right?
Yeah.
Why would your computer need to talk to other computers in the network? Yeah, sharing files back and forth. You probably need to talk to the domain server, right? Since that's where we got our packet tracer files and stuff from sometimes. You're also considering that that's for the computer, not just for you. So anybody else that logs onto that computer, all their ARP stuff's being learned too. So you can see how that stuff can kind of build and build and build over time. So there you have your addresses and your MAC addresses. Tell me about the internet addresses. What do they all start with? Huh?
Is that the MAC addresses?
No, the IP addresses.
1040.
10s, right? You see lots of 10s?
Yes.
Okay. All the computers on the wired network through TSTC, they all start with 10. So when you see 10, you see something that's a wired computer in TSTC. So that's one of the ways that they call it logical addressing, because you can logically tell something. by that IP address, depending on the way it was set up. And that's the way it was set up here. If you see something with a 172 on it, that means it's something that's wireless. And we'll talk more about that in the next chapters on. But that is all of the IP and MAC address associations that just your computer has made. If a whole bunch of computers are turned on at the same time, and they're searching the network at the same time, this can cause some strain. Once they figure out all the IPs they need, the congestion is going to turn to normal. So you could have what's called an ARP broadcast, where everybody gets turned on at the same time, and everybody's trying to figure out all the information they need to start sending things, and it might flood, cause some congestion on the network. You can fake a MAC address. You're not supposed to be able to fake a MAC address. It's supposed to be something that's burned in, but there are free programs and stuff online that you can spoof a MAC address with. So this is something that's really commonly used for attack purposes. We talk about IP security. So they may reply to an ARP request even though they're not actually that person, but they will spoof it so that it looks like they are. So they will just start sending all the things that were intended for that person on the network even though they're not that person. So that is a way that attacks can happen. It's also the way that, have you ever been at one of those coffee shops or internet cafes or something where you get 30 minutes or an hour of access and then they block you? They're blocking your MAC address. So you could technically sit there and spoof your MAC address every hour and get unlimited internet. But that's how they're checking. They're checking your physical address. And also, every time I say something like that, I have to remind you to use your powers for good.
You know what?
To use your powers for good.
Yeah.
Only for good, never for
But
evil.
the dark side has good.
I know. And they're chocolate chip. Okay, so that is chapter 5.